This video covers sections 2 and 3 of chapter 10, where we talk about doing inference for a quantitative variable using the t-distribution. We'll talk about constructing confidence intervals for the population mean using t. We'll compare the confidence intervals we get with the z-distribution and with the t-distribution. We'll talk about when neither z nor t can be used. We'll look at computing confidence intervals for different levels of confidence. And we'll talk about doing a t-test for hypothesis testing. We'll continue with that by comparing the z-test and the t-test, and we'll perform the t-test using our calculators. We'll talk about how large it takes to have a large value for t. We'll talk about doing the t-test when our n is small. We'll talk about the factors that lead to rejecting the null hypothesis, as well as the types of errors we can obtain. And we'll tie confidence intervals and hypothesis tests together. In the 4 stages of statistics, we are still looking at statistical inference, and we're doing inference for one quantitative variable using the t-distribution. Remember that for a fixed sample size n from a population with mean mu and standard deviation sigma, the sample mean is a random variable. The mean of that random variable is mu. The standard deviation is the population standard deviation sigma divided by the square root of n. And as long as n is big enough, the shape of the distribution is approximately normal. When we talked in the past about standardizing a sample mean, we standardized to z, that is the z-distribution or the normal distribution. If we know sigma, the standardized value for x bar is x bar minus mu in the numerator, sigma over the square root of n in the denominator, because that's the standard deviation for sample mean. If sigma is unknown, though, and n is large enough, that is at least 20 or 30, then the sample standard deviation should be close to the population standard deviation, and it's okay to simply replace them. Notice the difference in these two formulas. If n is not big enough, we don't know that the result of this computation, x bar minus mu over s over the square root of n, we don't know how close that is to z. So instead we use t. T is a random variable. It is centered at 0 because x bar is centered at mu. So when I do that subtraction in the numerator, I should get something close to 0. Like z, t is distributed symmetrically and bell-shaped as long as x bar is normal. But in general, t has more spread than z. That's because the sample standard deviation does not contain as much information in it as the population standard deviation. The t-distribution also has a number called the degrees of freedom associated with it. You can compute the number of degrees of freedom simply by subtracting 1 from the sample size. So how do we know which one of these to use? In general, if we're doing this by hand, we'll use z if we know sigma or if n is large. Otherwise, we'll use t. That is, if we don't know the population standard deviation and the sample size is less than 30. However, we'll get more accurate results whenever we're using software, that is calculators or Excel or some other software package. We'll always use z if sigma is known, and we'll always use t if sigma is unknown. Here's a look at the difference between z and t. Notice that t has thicker tails than z does. In the last video, we talked about constructing 95% confidence intervals for the population mean when we knew sigma. And we got it by the formula x bar plus or minus 2 times the standard deviation for sample means. That 2 came from the z distribution. Remember, it's the rounded off value for 1.96. The reason why is that 95%, notice this is a 95% confidence interval, 95% of normal values falls within 2 standard deviations of the mean. Now, if n is small, if we don't know sigma, we can't say that the 95% confidence interval is given by this formula, which is the same as the old one, except we've replaced the population standard deviation with the sample standard deviation. The reason is the area in the tails under the t distribution is bigger than for z. That means we have to go out a little bit farther to get to 95%. For the t distribution, when we don't know sigma, the 95% confidence interval is x bar, that's the sample mean, plus or minus some multiplier times the sample standard deviation over the square root of the sample size. The multiplier comes from the t distribution with n minus 1 degrees of freedom. In general, the multiplier is going to be bigger than 2. Multipliers for t are always bigger than the corresponding multiplier using the z distribution. When we talk about degrees of freedom, we're talking about a number that's associated with the t distribution. Why it's called what it is called is not really important for our purposes in this class. But many of the distributions that we're going to look at between now and the end of the semester, t, f, and chi-square, there's not one single distribution that has those names. The shape of the distribution actually is determined by the sample size or by some other number associated with the situation at hand. So each of these has a number of degrees of freedom associated with it. For t, the number of degrees of freedom is 1 less than the sample size. For example, take this random sample of shoe sizes for 9 college males. Let's compute the 95% confidence interval for the population mean. Well, if we compute the mean of the sample, we get 11.222. The standard deviation of the sample, and again that's sample standard deviation, S, is 1.698. The sample size is n, which means our degrees of freedom is 8. If we take a look at this diagram, we see 95% of the area under the t distribution corresponds to a positive t value of 2.31. That's the multiplier for the interval. So our interval is 11.222 plus or minus 2.31 times the standard error, which is the sample standard deviation divided by the square root of the sample size. That gives us an interval from 9.92 to 12.53. Let's compute that same confidence interval using our calculators. We'll start by entering the data into L1, 11.5, 12, 11, 15, 11.5, 10, 9, 10, and 11. It looks like I didn't get one of them right. That should have been a 15. Double checking. Oh, that should have been a 12. Alright, I think my data are good. So I'm going to quit out of that. I'm going to go to the Stat menu, and I'm going to go over to Tests. And what we're going to do is create a confidence interval using the t distribution. We'll find that under t interval. Now I have data in L1, so I'm going to leave this on data. If I just had the sample mean and the sample standard deviation, I could move the cursor over to stats and enter those directly underneath. But because I have data that are in L1, we're good there. Frequency list should be 1 also. Here I can change the confidence level. If I wanted a 90% confidence interval, I could do that here. And I'm ready to calculate. And our confidence interval is reported as 9.91 to 12.52. T-interval also gives you the mean of the sample and the standard deviation of the sample. Now, looking back at our confidence interval for shoe sizes, we got a confidence interval at 95% confidence of 9.92 to 12.53. We got that using the t-distribution. If that 1.698 that we got from the sample standard deviation had actually been the population standard deviation, then this would be a z standardization and a confidence interval using the z distribution. So we'll use 1.96 for the multiplier, which gives us a confidence interval from 10.11 to 12.33. How do these differ? Well, notice the different multipliers. The t multiplier is bigger, and it always will be. Notice the width of the t interval is about 2.6, while the width of the z interval is about 2.2. The reason for this is, if we know the population standard deviation, we have more information, so we're more confident about our results. That allows us to shrink the interval a bit. If we look at the student survey data and look at earnings, which had an average of 3,776 and standard deviation of 6,500, the t-multiplier for 95% confidence and 445 degrees of freedom is 1.9653. How different are the intervals now? Well, the t-multiplier is 1.9653. The z-multiplier is 1.96. Those are really close together. So both intervals will be about the same. Now remember that sample means are a random variable centered at mu with standard deviation sigma over the square root of n. The shape of the distribution is approximately normal as long as n large enough. Now, if sigma is unknown and n is small, then when we standardize, we get t. But what do we mean when we say large enough n? Now, we've seen this before. We can assume that the shape of x bar, that distribution for fixed sample size n, is approximately normal if one of the following hold. If the sample looks like it's normally distributed, or if the sample seems to be symmetric and n is at least 15, or if the sample is no more than moderately skewed and n is at least 30, or the sample data are very skewed but n is much larger than 30. If none of these hold, then that formula that we use to find t is not t. That formula only results in t when x bar is distributed normally. Here are the number of credits taken by 14 non-traditional students. You can see the histogram below. If I ask for a 95% confidence interval for population mean, what would you tell me? Well, because n is small and the shape of the distribution is very left skewed, we can't use t. Something called non-parametric methods can be used to find this confidence interval, but we won't be covering that in this course. Now, this chart excerpts some of what you see on the handout that I gave you. What I want to point out again is that for a lower confidence level, the multiplier is smaller than for a higher confidence level. Notice that for any value of df that we choose, for any number of degrees of freedom, the t multiplier is bigger than the z multiplier. And as the number of degrees of freedom increases, that is, as n increases, the value of the t multiplier gets smaller and in fact approaches the z multiplier. So remember our random sample of 9 shoe sizes. What t multiplier will we use for 99% confidence? Well, we find 99 on the table. It's right here under our distribution. We find the corresponding t value and we see it's 3.36. You can also read that off your table, or you can use your calculator to compute the confidence interval or the multiplier. So for our shoe example, our 95% confidence interval went from 9.9 to 12.5. What would the 99% confidence interval be? Well, the multiplier for 99% confidence and 8 degrees of freedom is 3.36. So when we put that into the formula, we get an interval from 9.3 to 13.1. Notice the width of the 95% interval is 2.6, but the width of the 99% interval is about 3.8. In general, to get higher confidence, we need wider intervals. So to sum up confidence intervals using the t distribution, we compute the confidence interval for this population mean by taking the sample mean and adding and subtracting our multiplier times the standard error. That's the standard deviation in the sample divided by the square root of the sample size. The multiplier depends on two things. It depends on the sample size, which when we subtract 1 gives us the number of degrees of freedom. As n goes up, the multiplier will go down. It also depends on our confidence level. As our confidence goes up, the multiplier goes up. Also note that a larger spread in the sample results in a larger sample standard deviation, which results in a larger margin of error. So what would make our interval narrow? A big N, because that affects the number of degrees of freedom and it makes for a bigger denominator in that fraction. A lower level of confidence, or a smaller standard deviation. Now let's bridge the gap from confidence intervals to hypothesis tests. Remember, a confidence interval uses a multiplier that comes from the t distribution with n-1 degrees of freedom. That multiplier is based on converting the confidence level to an inside area under the t distribution with appropriate degrees of freedom. Hypothesis tests will compute a p-value that's based on the tails of the t distribution, not the inside area but the outside area, again with n-1 degrees of freedom. Let's say that in one test with a very large n, we have a z-score of 2. Another test with 18 degrees of freedom has a t-score of 2. How would the p-values compare? Well, for z, the p-value ought to be just under 0.025. That's because there's 95% of the area inside 2 standard deviations from the mean, so there's 5% outside 2 standard deviations from the mean. For the t distribution with 18 degrees of freedom, the p-value is a little bit bigger than 0.025. So here's the comparison. We see z's above, and a z-score of 2 would fall just under the 0.025. But for t, With sample size 19 and 18 degrees of freedom, we see that 2 is actually a little bit less than the same number. That gives us an area a little bit bigger than 0.025. So looking at that t curve with 18 degrees of freedom, here it is with the relevant critical values highlighted. Would a t value of 3 be extremely big? Well, yeah. 2.88 represents kind of the biggest cutoff that we have, which corresponds to an area of half of 1%. Now, if we need to do a t-test by hand, here's how we'll do it. Here are the weights of 19 female college students. The population mean reported by the National Center of something that has an H and an S in it is 141.7. So looking at our sample, do we have evidence that the population that we pulled from is different from the NCHS population? Well, let's take a look at our hypotheses. The null hypothesis is that our sample is just a regular ordinary sample. Its mean ought to be 141.7. The alternate hypothesis is that something weird's going on, that the mean is less than 141.7. Let's check and make sure that we can use the t distribution. To use the t distribution, sample means need to be normal. Here the population is greater than 10 times the size of the sample. The shape of weights, if you take a look at it, they tend to be clustered in the middle. So a sample size of 19 is okay. The sample mean is 129.36 with standard deviation 12.82. So converting to a t-score, we'll take the mean in our sample minus the the null hypothesis mean, and divide by the standard error. That's the standard deviation over the square root of the sample size, and we get a t-score of negative 4.19. The p-value for that must be really small because 4.19 is a really extreme value of t. So we reject the null hypothesis. Our sample comes from a different population, or some values were underreported. So remember, to standardize a sample mean to a t-value, which is what happens when we don't know the population standard deviation, looking at this formula right here, we take the mean of the sample, subtract the purported population mean, and divide that by s over the square root of the sample size. The distribution of t is symmetric and bell-shaped, centered at 0, and we need to rely on the number of degrees of freedom, which is n-1. So remember that we will use the t distribution when we're doing this by hand, when the sample size is small and the population standard deviation is unknown. If we're using our calculators or Excel, we're always going to use t if sigma is unknown. Let's look at an example. With the same random sample of shoe sizes that we've seen before, is it plausible that the mean shoe size of all college males is 11? Here we'll use software. Our proposed mean is 11, and we're using the not equal alternative because we don't have any reason ahead of time, and there's nothing in the question that makes it sound like our sample is unusually big or unusually small. Here are the results. Notice you see a t and a p there. It's okay that we're using a small sample size because shoe sizes are distributed normally. Is t large? No. Is p small? Also, no. So can we believe that the population mean might be 11? Yeah, sure. With our calculators, using the same set of data that we used before, we can perform the same t-test. I'm going to go to the Stat menu, and I'm going to go over to Tests, and option number 2 is t-test. I'm going to input data, but if I had statistics instead, I could select stats and use that instead. Our proposed population mean in this case was 11. We're trying to see if our sample gives evidence that the population mean is different from 11. Our data are in L1. We'll use 1 for their frequencies. The appropriate alternative hypothesis is selected, and we'll calculate. Notice that we got the same t-value and p-value as was reported on the last slide. Remember when we were talking about the z-statistic, we used the 68, 95, 99.7 rule to talk about how unusual a value for z might be. Here are our guidelines. Notice that borderline between unusual and not unusual was around 2. For t, though, notice that sort of the borderline, which would be 2 for z, can be near 2 as well, but as the sample size goes down, it can also be up near 3. Now, for very small samples, we can assume that the shape of the sample means is approximately normal if the graph of the sample data appears normal. For a normal population, then this statistic that we compute is exactly t. So here's a random sample of 4 math SAT scores with mean 637.5 and standard deviation 87.3. Do they come from a population with mean above 500? Here we're using alpha as 0.05 as usual. Here n is small, but it's okay to use t because SATs are distributed normally. We punch this into our calculator and we get a t-score of 3.15 and a p-value of 0.02. So can we reject the null hypothesis? Sure. Can we conclude that the population mean, the population that we took this sample from, has a mean greater than 500? You bet. Now, looking at the same sample, do they represent a population where the mean is different from 500? Well, this is a different alternative hypothesis. Here we're using a two-tailed alternative, or two-sided alternative, which doubles the p-value. If our cutoff is 0.05, we no longer reject the null hypothesis, and we can't conclude that the population mean is not equal to 500. We think that it could be 500. Remember that t near 3 can be considered borderline, and here it is borderline. Look at that p-value, if n is really small. So remember that when we looked at these two hypothesis tests, a one-sided and a two-sided, the one-sided resulted in a rejected null. The two-sided did not result in a rejected null. Suspecting ahead of time that the mean might be greater than 500 made our results significant. That creates a concern. Our test failed to reject the null hypothesis on a two-sided alternative. So, should we believe that 500 is a plausible value for the population mean? Well, looking back, if the students from which we took this sample were students that had been admitted to a university, for example, we would expect their scores to be higher than those who weren't. Because 4 is a very small sample size, we have to worry about a type 2 error. That's a false negative. Is it important that we stick to 0.05 as our cutoff value? No. It's possible, since we're talking about math SATs, we can find the population standard deviation and perform the z-test. Do you think that a mean of 500 for the population seems plausible when the smallest value that we see is 570? I don't think so. So these are the concerns that we run into, especially with very small sample sizes. So now let's take a look at some factors that lead us to reject the null hypothesis. What things will increase the likelihood that the null will be rejected? Well, remember, the more extreme t is, the more likely we are to reject the null. T is computed in this way, this formula over here on the left, but after we do a little bit of algebra, it simplifies to that formula on the right. So what can make t big? Well, if that difference inside the parentheses in the blue box, if that's big, which means the sample mean and the proposed population mean are very different. As n gets larger, that square root of n is going to get larger. That makes t larger. If the standard deviation is small, it makes the denominator of that fraction smaller, which makes t larger. All of these things will increase the likelihood that we reject the null hypothesis. Similarly, if the sample mean and the population mean are close together, then the quantity inside the parentheses up there in the numerator will be small. If the sample size is small, and if the standard deviation is large, all of those contribute to making t smaller. That small sample size is what we just saw in the previous example. That small sample size can lead us to a type 2 error. Remember, that's a false negative, a failure to reject a false null hypothesis. It's possible in several instances that we end up with a type 1 error. That's when we reject a true null hypothesis. So, looking at verbal SATs with mean 500, a sample of 20 scores each in 100 schools gives us this test. We have our null hypothesis that the mean is 500, and the alternative that the mean is less than 500. If we reject the null hypothesis in 4 of those schools, can we conclude that the mean verbal SAT in those 4 schools is significantly lower than 500? Well, if we're using alpha equals 0.05, then in the long run, we expect to commit this type 1 error about 1 in every 20 times. So over 100 schools, we would expect around 5 null hypotheses to incorrectly be rejected. Since we rejected 4, this seems reasonable. So remember, our confidence interval is a range of plausible values for the population mean. The hypothesis test decides if a value that we propose is plausible. So, if the proposed mean is in the confidence interval, we won't reject the null hypothesis. But if it's not, we will reject the null hypothesis. So take a look at these confidence intervals. Here's the 95% confidence interval for population mean earnings, for population mean shoe size, for population mean math SAT. What can we conclude about these hypotheses? First, that the population mean is 5,000 versus that it's less than 5,000. That the second one is 11 versus not equal to 11. that the third one is 500 versus not equal to 500? Well, in the first one, the proposed mean is outside the confidence interval, so I think the null will be rejected. For the second one, notice 11 is right pretty much square in the middle of that confidence interval, so I doubt that the null hypothesis would be rejected. Now in the third one, that mean is very close to the borderline. So we'll have to actually run the test to see for sure if the null will be rejected. In summary, the t confidence interval for population mean chooses a multiplier from the t distribution with n-1 degrees of freedom. We talked about when to perform inference with z versus t. We talked about constructing confidence intervals from the t distribution both by hand and with software. We looked at the comparison between z and t confidence intervals. We talked about when we can't apply either one of these techniques. We talked about finding other levels of confidence besides 95%, and we transitioned from confidence intervals to hypothesis tests. And we talked about doing the t-test by hand. Then, after we compared the z and t distributions again, we talked about how to do the t-test with our calculators. We talked about what it takes to make a large value of t considered to be, quote, large. We looked at performing t-tests using small n's, both one-sided and two-sided. We looked at several factors that can encourage us to reject the null hypothesis. We talked about type 1 and type 2 errors and how multiple tests will result in a type 1 error with probability equal to our cutoff, our alpha. And we related the results that we got from our tests with corresponding confidence intervals.